Yeah, comes on everyone. Let's start off. There, the last thing that we did, we started with refraction. Great, let's go ahead with the problem. So we have a medium here, mu1 and mu2, and mu1 is greater than mu2, so light ray is going from denser to rarer. So if you send a light ray, it goes away from the normal. This is your angle of incidence, and this is your angle of refraction. Plot the graph between deviation versus I graph. You know the deviation, right? The angle between the, so in this scenario, the light ray would have gone straight, but you have gone this way. So this is delta. This is a good question. I mean, it's a standard mains or a bits level question. Should definitely remember the graph. All others, keep your cams on. Let's give it a try. Take a minute. Approximately how the graph looks. See, when you draw graphs, only there are only two things you need to ask yourself. Is it a straight line or a curve? If it is a curve, it is an upward curve going or a downward curve, meaning if it is like this or it is like this. So you don't need to know exactly how the curve looks. So if there are two cases, you have to be careful here. Meaning, this is something I keep telling you. When you draw the graphs, you should know how to eliminate them rather than actually drawing the graphs. Now you will realize something like this. There are actually two scenarios here. If you go I less than theta critical, this is I, this is R, and if you use the Snell's law, mu1 and mu2, mu1 sin I is equal to mu2 sin R. So from here we get R is equal to sine inverse mu1 by mu2 sin I. And the deviation would be R minus I. So yeah, this is not a straight line for sure. This is some weird thing. But once you cross the angle I greater than theta critical, now there'll be a TIR. The light ray will simply bounce off like a mirror. Now the deviation would be, you would have gone straight. So this is I and this is I, and this angle would be delta. We can clearly see delta is 180 minus 2I. This is a straight line. This is looking like y is equal to mx plus c. So this much if you figured it out, right, then you can actually eliminate from the option. So the first part of the graph, so the graph will actually divide into two pieces up to theta critical. So the first part of the graph would be some curve. it would be an increasing function, right? The deviation would keep increasing because r will increase faster than I. So r minus I is increasing function, isn't it? Think about this. Mu1 is greater than mu2. So whatever is the angle of I, this will be always greater than that. So r is increasing faster than I. So, and the biggest hint comes from here. At theta critical, see what happens. Exactly at theta critical, the light ray would go like this. The moment you increase the angle by little, suddenly the light ray becomes like this, meaning the deviation would suddenly bump up. It would go up somewhere here and then it decreases. This is how the picture would look. Is that making sense? Look at this. Exactly at theta critical, this is the light ray. If you increase the angle by 0.1 degree, suddenly it becomes like this. So this angle suddenly bumped up, it increased by this amount. There's a sudden rise. So there's a discontinuity function. That is how the graph looks. All clear with this. Clear with this? That's your delta versus I graph. So main idea is to figure out there'll be discontinuity in the middle. There'll be a TIR. So you have to include all that. And that's what makes this question good. But standard result, you should definitely know this stuff. All clear with this? Any doubts on this? Advai, clear with this? Aditi? Shayan? Next one.
सर
Yeah.
सर लास्ट क्वेश्चन में हाउ डू वी नो कि वो अप कॉनकेव है कि डाउन कॉनकेव?
You're not there again in that class. P tak maine almost for 5 minutes I was shouting that only. What did I say? The function is increasing faster than I. It is an increasing function. So the slope would have to keep increasing, isn't it? Think
So
about it,
it
na.
can
If
still be
the
increasing
function,
na, with slope
hey,
decreasing.
then I think the only way to check it out is iska differentiate karo with respect to I and then figure out.
Okay, sir.
And that's if you want to prove it mathematically, then you have to do d delta by di. And then, yeah, sine inverse function. I'm not sure how we'll differentiate that. So you have to differentiate and check it out mathematically. But take like this thing. If you say the function is going like this, imagine the graph would have continued. What would have happened? This would eventually, right, either will take a turn down or will become constant, isn't it?
Sir, it can still keep increasing. Like
Then I think
ln.
you have to just check it out mathematically. Then there's no other way.
Okay, sir.
There is no other way to guess it then. Function is increasing. But anyway, so remember that. This is mu is equal to 2, name mu is equal to root 3, mu is equal to 1, and mu is equal to 1. This is your light ray, and you're sending at 60 degrees. Plot the path of the light ray. Draw the path and find deviation. Hmm, Let me see if I can figure out an easier way without mathematics. But for now, remember the graph looks like that. And that's a valid confusion. Let's give it a try run. This is an easy one. Let's see. Yeah, right. Deviation is 60. Right, Arya? Right, Samya. Look at this thing. So for the sphere, the normal is this blue line. Apply the Snell's law. Mu1, that is 1 sine 60 is equal to root 3 sine r. Sine r would be half. R is equal to 30 degrees. So this light ray would enter here at 30 degrees. And then it will go hit the thing somewhere here. So this would be the normal again, and this would be the normal again. And you can clearly see this is radius r, this is also radius r. It is an equilateral isosceles triangle. So this also has to be 30 degrees. If this is 30 degrees, you again get this would be 60 degrees. And 60 degrees, if you see, and this would be 120 and this is 60. So it actually becomes parallel to it becomes horizontal because this is 60, this is 60. That means this is horizontal to this base. And that is how the light ray will look like. And what is the deviation? You are going like this. This is your final ray. And initially you are going something like this, extended forward. This was 60 and this was 60. So this was the green one was the initial. The red one was the final. So this angle is your deviation. Delta is 60 degrees. So the light ray has deviated 60 degrees clockwise. Clear with this? So a simple Snell's law, and you just have to do that thing there. Any doubts on this? Clear? Snell's law, a little geometry. Next one. These are straightforward questions. We are just using Snell's law there. Let's say we have a swimming pool of depth d. Refractive index is mu of the liquid. At the bottom of the pool, there is a bulb of power P. Outside, we can take it as vacuum mu is equal to 1, and we have an observer who is standing outside the lake. Now, what happened? Now, what we think, right? The whole light rays will pass through the pool and the whole pool will be bright. But in reality, this observer actually sees a patch of light. He doesn't see the whole pool is bright. He will see a patch of light on the surface. So the whole swimming pool ka surface will not be illuminated. Yeah, there will be some dispersion and all. We are ignoring that. An observer sees a patch of light on the surface. Now you need to ask yourself, why is this guy seeing only a patch of light? Why is that whole surface not illuminated? That is something you need to figure out. Find the area of that light patch. And if P is the power of the bulb, how much power is coming out of the liquid surface? If the bulb is emitting power P, how much energy is being coming out of the surface? So the first question is this. He is not seeing the whole surface bright. He sees only a part of the swimming pool is bright. So you need to ask yourself why. And then we need to see then what is the area. Right, Samir. Right, that is the logic there. So what is happening exactly? If you look at the light rays, so the light ray which is going straight, this thing goes off because I is equal to 0. The light rays are going from denser to rarer. So if you see they start refracting, at some point, you get a theta critical. At this point, theta critical. Now, after this, any light ray which hits the surface will bounce inside, isn't it? That is the reason the light rays after this point are not coming out. That's what was happening. So any light ray after this is simply bouncing inside. You don't see any light rays inside. So rays incident at an angle greater than theta critical, they bounce back into the water. So the rays incident greater than theta critical. That's the reason you don't see the whole pool is bright. You see only a part of it. And how will this surface look like? So this is the light ray going up. This is your theta critical. Similarly, you'll have one on this side also, theta critical. So this will be actually happening in three-dimensional. What you get is a cone, the patch of light. You'll see a circular disc on the surface of the water. Is that making sense, everyone? So the light rays will go in a cone kind of thing, and you will see that thing. So that's your theta critical. This is also theta critical. This would be your radius, and tan theta critical is equal to r by t. From here, we get the radius is equal to d tan theta critical, and the area will be pi r square. And how to get the theta critical? Mu sine theta critical outside is 1 and sine 90. So there, from here we get sine theta critical is 1 by mu. If you know sine, you can find tan theta. You make a small triangle. This is 1 and this is mu and this is root over mu square plus 1. No, I wrote wrong. Wait, 1 and mu. This is the root over mu square minus 1. So tan theta critical is 1 by root over mu square minus 1. Have a look at this. All clear with this? So the main idea is that you are having a TIR and that is the reason all the letters are not coming out. Now what about the power ka part? Now the power ka part, think of like this. Imagine there was no water. What would have happened? These light rays, if imagine there's nothing there, if you just have the bulb at the center. So this bulb B is generating power P in all directions. So you're having power P in all directions. Now your disk which is there, the disk is in this part of the area. Now, can I argue this way? Every light ray that is passing through the disk is also passing through this surface, kind of like projected area. So this is how we can argue. So if you look at this curved surface here, the power passing through that curved surface is the power passing through the disk. Same photons will pass through them. In electrostatics, we saw this thing as flux, if you remember. Passing through that shaded area is same as the power passing through the disk. Because the photons are same, the same amount of photons will pass through them. Right? So this is how the picture would look like. This was the disk. And this top part, right, would be like a spherical part. So this is a part of a sphere. And this angle was your theta critical. That's a part of a sphere, and that is the area there. And what is this area there? 2 pi r square 1 minus cos theta critical. This we have done in calculus and electrostatics of flux. Now unitary method. So for total area of 4 pi r square, how much power is going? P. For an area of 2 pi r square 1 minus cos theta, how much power is going? So this is the power through the disk. So power through the disk will be P by 2 into 1 minus cos theta. This gives you the same vibes as a flux. If a charged particle Q is there at the center, find the flux passing through the disk. Formula yaad hai? Q by 2 epsilon 1 minus cos theta. What is the total flux? Q by epsilon. So Q by epsilon flux is looking like power. Is this making sense, everyone? So the same question, if I had asked you like this, there is a sphere and there is a point charge plus Q here. And if I say there is a disk here, the flux passing through the disk is Q by epsilon 2 epsilon 1 minus cos theta. So you can see the vibes look the same. So the flux through the sphere is Q by epsilon. So Q by epsilon is like power, and that thing is looking like that way. Is this clear, everyone? Yeah. So in case you forgot about this, you should go back to Gauss law. This is where we did the flux passing through the disk. We did a lot of problems on that. Clear with this thing, power part? Next thing. We got a glass slab, thickness D, and this is mu. You're sending a light ray through this. This is I, it will hit somewhere here. This is R, and then it comes out. So if you extend this light ray, you would have gone like this. So this distance here is called lateral shift. And if you notice something here, if that is R, this is also R, and this is also I. So basically the light ray will come out parallel to itself. So if you send a beam, it will go inside, it will bend inside, but when it comes out, again, it becomes parallel. But the light ray will shift a bit. So the deviation is 0. Find the lateral shift. So this is a very interesting thing. So when you pass through a slab, you'll go with I, you'll come out with I, but it's not parallel anymore. It's shifted a bit. It's still parallel, but shifted a bit. How do we find the lateral shift? Is that clear, everyone? The final ray is parallel to the initial ray. The deviation is 0. When you pass through the slab. So when a light ray passes through a slab, there'll be no deviation. T sine I minus R cos R. Yeah, something like that. It's mostly geometry there. So you can keep trying. I'll show you. So this was your normal. So this light ray was entering here, then it has gone like this, and then it has gone like this. Okay. So I drop the line here. This line would have gone like this. Perfect. So what you want to find is this distance. If this angle of incidence is I, and if this is R, then this angle of incidence will be I minus R. Let's call this point A, let's call this point B, let this call point C, and let this call be D. So in triangle ABC, and this distance is D, cos R will be D by AB. So from here I got AB is equal to D sec R. Then when you take the triangle ABD, sine I minus R will be BD by AB. But AB is nothing but that's your lateral shift, D sec R sine I minus R. There, it is all about putting the angles in geometry. There is really not much. It looks weird, but it's not that easy to do it. Clear, everyone? Yeah. Next thing. Now, if you extend this further, this is a very good result. What if you have multiple parallel slabs? Mu1, mu2, mu3, and so on till mu n. And let's say outside is mu m and mu m. Now, if you try to send a light ray inside this, now see what just now we said. When a light ray passes through the slab, it doesn't deviate there. And so basically, if you enter here at an angle theta, this angle would be R1. Then when it comes and hits here, this angle would be R1. When it comes out here, this angle would be R2. And when it hits here, this angle will be R2 and so on. Eventually, it comes out with the same angle, theta. So apply Snell's law for each interface. So initially, it will be mu m sine theta. That would be mu1 sine R1. For the next interface between 1 and 2, R1 becomes the incident angle and mu2 sine R2 becomes the refracted angle. For the next thing, it will be mu3 sine R3 and so on is equal to mu n sine Rn. So it's a very good result. So for parallel slabs, mu into sine I remains constant. That means if they give you 100 slabs and they ask you what is the deviation at the 50th slab, you need not do for each and everything. Take one and take 50 directly and get the angle from there. Is this clear, everyone? So refractive index of that slab and the incident angle on that slab, that product will always remain constant. Now, one thing that comes here, what is a normal? When you say this is the normal, exactly how do you define what is a normal? For example, let's say we got a slab where mu is changing as 1 plus x. So here the refractive index, right? 1 plus x square, let's say. It is increasing with x. This is x and this is y. That means at a given y coordinate, x coordinate, the whole will have same refractive index. So these are like thin slabs like this. Suppose if someone gives you mu is equal to 1 plus y square, that means for a given y coordinate, the whole thing will have same refractive index. That means the slabs are like this. And how do you define normal? The normal is in the direction in which the mu changes. Since here mu is changing in x-axis, so the normal will, pass through the interfaces. So this is the normal. If mu is changing in y direction, then the normal is in y direction. So yeah, useful one. So when you say the normal at an interface, it is in the direction in which the mu changes. If mu changes in x, then x-axis is the normal. All clear with this? Any doubts on this? No, the actual question on this. So you need to know all the story for this question. Let's say I created a hypothetical medium. The whole first quadrant is filled with a refractive index mu, which is equal to root over 1 by 4 plus 1 by y square. Right? This is hypothetical because if you see mu is coming less than 1, but I want to get a good equation, so I created an hypothetical function there. So we got a median there. So the entire mu is changing on the right hand side. Everywhere else, mu is 1. Now you sent a light ray through the origin at an angle of 30 degrees. This light ray started bending inside. Remember, light ray goes in straight lines in homogeneous medium. Here the light ray is not going in a uniform medium, so it starts bending. Something like this is what actually happens in a mirage. If you ever heard about mirage, right? So that's the catch there. So the whole quadrant is filled with this medium. Find the equation of the light ray. Find the equation of the light ray in the first quadrant. There. So this is like parallel slabs, isn't it? The slabs are in what? X-axis. The process is same. Like they can give you any weird equation, but it works. How do we handle this? This thing, if you remember, I told you this multiple times. Whenever they ask you find the equation of something in physics, first time, where did you hear this thing? I think it started somewhere in fluid mechanics. Find the equation of the curve. And what we did, there's only one thing that we know. Yeah, kinematics alag hai. This is a different equation of the shape of something and all. We know slope is dy by dx. So somehow you have to get tan theta using physics and then put dy by dx and integrate. The second time you saw something like this was in elasticity. This question, if you remember, find the equation of this curve. देखो ये पे भी वही किया था. We got that slope and dy by dx and we got this. So the theme is always the same. Somehow I need to get the slope of this line, slope of a tangent, and then figure it out. So this is how it would look. So this light ray is entering here and it bends. Okay. So take some random point here, x comma y. The normal will be in the direction in which the mu changes. Here mu is changing in y direction. So this is your normal. At this point, this green line is your tangent. Don't get confused now. This is not normal to the curve. This is a tangent to the ray that is normal to the medium. So don't get confused between these two. This is a normal to medium. This is not normal to the ray. Okay. Then this angle would be your angle of incidence I. If that is I, then this angle is 90 minus I. And we know from Snell's law, mu into sine I is constant. So initially this angle was 30, mu is 1, so 1 sine 30 is equal to this mu, which is root over 1 by 4 plus 1 by y square into sine I. Sine 30 is half, so from here I get sine I is equal to, that is half, so you can cross multiply this. This will be half into root over 4y square by 4 plus y square. That comes out to be y by root over 4 plus y square. This is your sine I. This would be y, and this is 4 plus y square, and this is your 2. Now, what is the slope of the tangent? Tan of the angle with the base, which is tan 90 minus I, which is cot I. Cot I is nothing but 2 by y. But slope of the tangent is dy by dx. Integrate this on both sides. Y dy is equal to 2 dx. We get y square is equal to 4x. This is a parabolic curve, which is hypothetical. You will never get this because that refractive index is messed up. If I put y0, I'm getting mu infinity. As y tends to infinity, mu is becoming 1 by 4, half, which is less than 1. Doesn't make sense. So this is some region, where mu has to be less than 1. So it is some kind of a slab. So I made up these numbers to get a good equation. And I get really bad equations. But is the process clear, everyone? So the light ray is going some weird curve. So draw a tangent, find the angle of incidence, let it be I, then use this one to get the relation sine I, and then put it back. All clear with this? This is a good one. This is a refraction in a non-homogeneous medium. So light rays don't go in straight lines, they do bend. If I change the equation, it will go in a different curve. Because here mu is changing slab-wise. Now you can make this problem even better. You can take it to the higher level. So let's say we got a sphere. radius r. This is a weird medium. So here the medium, right, mu of r is given by mu naught small r by capital R. This r ka value lies between infinity to capital R. Mu naught is a constant. Small r is a distance from center. Meaning, look at this medium here. As you go away from the center, the refractive index is increasing more and more. Meaning it is like shells. So each shell has a different refractive index and it is increasing. Can you tell me the direction of normal here? What is the normal for the medium? In the direction in which mu increases, isn't it? So यहाँ पे normal क्या होगा? All these, right? The lines passing from the center, all these are normals. This is how the normals will look like for this medium, radial direction. So we have a system like this. Now what you did, you sent a light ray. This is your incident ray. So from the center, this was your normal. This distance was 3r. So this light ray at a distance of 3r, it entered here. And this is your angle of incidence theta. So you sent a light ray at an angle theta at a distance of 3r. And what happens, because the medium is non-uniform, it starts going in some curve. I don't know, it will go in some weird curve. Find the minimum distance between the light ray and the center. So at some point here, the light ray, right, this will be your minimum distance. Find the minimum distance. This would actually go something like something like this. So it'll come closer and it'll fly away. Now, just to give you a little warning here, mu into sin I is not valid. This is derived for parallel slabs. Here it is radial, right? This is valid for slabs. You derived this when you had medium was changing for slab. Here it is changing radially. So you can't use this formula anymore. So we need to derive a new relation between mu and I. This would be a really good question. So advancement, this is the kind of questions like even at an advanced level, this will go. It's a good question. The previous one, it's also a good question, but yeah, at an advanced level, people can handle it now. Listen, so we need to get a relation between them. Now we can do this, using little geometry. I can find a relation, but it's a little weird. Well, I really don't like that, but I'll give you an idea later on if you want. But let me use something which I taught you last class. You want to guess what I'm going to use? Law of conservation of angular momentum. See, so last time we said the light rays are simply made of photons. So now, if this was your normal, and if a light beam is incident at an angle and it bounces off like this, so this is your angle of incidence and this is your angle of refraction. And this was your normal. And last time we saw, right, the forces due to the photon will be only along the normal. When you're passing through the same medium, you won't have any force. But when you cross the interface, you have a force. If you remember last class in Fermat principle, this is what we said. The horizontal momentum is conserved. So there is a force in the vertical direction, right? So the force is along the normal. There is no force in the horizontal direction. So this is the first thing you should have an idea there. So that means we know the forces due to these photons are along the normal. Therefore, the torque about the center is always zero. If the force is always passing through the center, then the torque is zero. Therefore, the angular momentum of these photons about the center is conserved. And we know angular momentum is nothing but r cross p. P is your momentum, which is r into p into sin I. And last time I showed you what is momentum. Momentum of a photon h by lambda multiply and divide by c. This becomes energy by c. So this would be distance r. This would be energy by c of the medium, which is c by mu into sin I. Energy of a photon doesn't change because it depends only on the frequency. So mu will go up. You end up with mu into r into sin I. C is also constant. Is constant. This is the relation mu r sin I. So when a light ray goes from the radial region, this thing remains constant. It is not mu into sin I anymore. It also depends on the distance r. This is your law of conservation of angular momentum. And how to do this mathematically, I'll just show you what. See, so we take a small region there. So from here, I'm drawing big here, but this is a very thin region. So remember that momentum stuff and all, it's really useful, like, because you guys are fine with mechanics, right? So it becomes really useful there. Now, if a light ray enters here at an angle I1, and then when it goes like this would be your R, right? And this would be your new angle of incidence I2. That's your normal there. Then we use little geometry here. So if that is I2, this will be 180 minus I2. Now, this is the center. Let's call it O, A, and B. So in triangle OAB, if we use the sine rule, R by OB, I'll do one thing. I'll take the distances also. Let this distance be R1 and let this distance be R2. Great. So R by sine R, R2 by sine R. is equal to R1 by sine 180 minus I2, right? So, and from Snell's law, so we get from here R1 by R2 is equal to sine I2 by sine R. This is one equation. From Snell's law, we know mu1 sine I1 is equal to mu2 sine R. Take sine R and substitute there. This is equation 2. Substitute here. That would become mu1 by mu2. Mu2 will go up. You end up with mu1 R1 sine I1 is equal to mu2 R2 sine I2. Therefore, mu sine R is equal to constant. This thing, I know how to do this, but it never clicks. Take a triangle, take a small region. Since this thing is very small, you can assume approximations. This is how you do mathematically. But this is better, isn't it? So if you talk in terms of photons, suddenly life becomes pretty easy. And once you got this, the question is over. So the light ray, let's just get the picture from here. So this is your D minimum. Angle would be what? 90 degrees? Yeah, 90 degrees. That is a normal, and that is the light ray going like this. So this is 90 degrees. So mu1 R1 sine I1 is equal to mu2 R2 sine I2. Initially mu would be, that is 3R. So mu naught into 3R by R, because mu is given as mu naught small r by capital R. And what is the distance there? The distance is also 3R, and the angle is sine theta. Mu2 will be mu naught. I don't know that. So that is D minimum by R, and this is also D, and this is sine 90. Mu naught will go off. Then you end up with 9R square sine theta is equal to D square. So D is equal to 3R root sine theta. Is that clear, everyone? So getting that mu R sine I constant was the headache. Once you got that, then it is easy to solve. This is a variation of the previous question. In a previous question, it was going in slab. Now it is going in this way. So tomorrow, if they say there is a, a line charge kind of thing. So there's a light in the form of an infinite line, and the lighters are going in a cylindrical region. You can still use your momentum stuff and all. It still works. Clear with this? Law of conservation of angular momentum. It's a good question. Definitely check it out again once more. Do it. Do it on your own once or twice, and then you will become comfortable with it. But you don't like that, mathematically you can do it. I don't like this. So up to you, whatever you prefer. The next thing, apparent depth. So what is this apparent depth? Let's say we have some liquid here and we have an object at the bottom. Now, if you see the light rays here, this light ray will go straight and these light rays will deviate a bit. So when you extend them, the person who is outside will start thinking this is the image. I'll exaggerate a little bit. So for a person here, he will feel that is an object there. This is an observer. This distance is called H apparent. We're not going to derive it. It's a lot of approximations there, and this is H. It's not really that important derivation. So this is the main formula which you need to remember. So the apparent depth, so that is where you think it is there. is given by h by mu object into mu observer. So you can read like that. So mu object is the light rays from where they're coming, and mu observer where the light rays have refracted. Now there are a few things here. This is valid only for paraxial rays. That means it is valid if the line joining object on the observer is perpendicular. So the observer should be as close as possible to the vertical line. What if it is not perpendicular? What if it is not paraxial? There is a way to do, but it is way beyond our thing. Maybe we will see later on during advanced ka thing, but now it is too much. And weirdly, they did ask in 2020 advanced, but it was so lengthy and it was so long. It's a waste of time. So we will see that later on. It's little irrelevant for now. So meaning when I say something like this, so it is going like this. The writers are spending really much. You need more data on this. Then the observer is not standing on top of it. Observer is somewhere here. So you're observing these light rays, something like this. And these are not paraxial. So don't use the formula for these cases. And the second thing, all distances, right? When you got that h apparent and h, these are measured from the interface. They're not measured from the observer. Clear? So this is how it would look. You must have noticed it, right? If you put a coin inside of water, it feels like it is a little higher. Look at this picture here. This straw, which is coming here, is supposed to actually go straight like this. But when you see it from the side view, it looks like the straw got bent. You're getting it? So technically, this part of the straw was here, and that is looking like it is here, and this is looking here, and so on. So there is a shift there. It should be even more below there. Kind of like this. Clear with this? Great. So let's see one small question so that you get used to the formula. So we got a liquid here. We got a fish here. And we got a bird here. The distance between the bird and the water is h, and the depth of the fish is capital D. The refractive index of the water is mu, and outside it is 1. They're exactly on top of each other. Find apparent distance of a fish as seen by the bird. Now, meaning who is the object and who is the observer? That is a question you should always ask. Fish as seen by the bird. Who is seeing? The bird is seeing. So bird is the observer. Fish is the object. Bird as seen by the fish. The fish is the observer and bird is the object. So one guy is in the water and one guy is in the air. Get this thing. What will they think? If you ask the fish, where is the bird? What will it say? And if you ask the bird, where is the fish? What will it say? Hmm. Let's see. This is how you do it. Okay, it is understand. Go step by step, then it will be more clear for you to see you. Let's see the first part. So who is looking at whom? The fish is seen by the bird. The bird is your observer. The fish is the object. Okay. Now listen carefully. So the light rays are going from the fish to the observer, right? So always start from there. Rays are going which way? Rays are going from fish. Now, if I ask you this question, suppose you are also inside the water, and if you stand here, and if you ask this person inside the water, boss, where is the fish? What will he say? He will say the fish is at a depth D, because you are in the water, fish is also in the water, you think it is D. Getting it? Now, if you just put your head outside, so this formula, right, is valid only when you are changing the medium. Are you getting it? The moment you put your head outside, you know what this person will say? This person will say, now he will use this formula and say, okay, this is D, the object is inside the water, this is mu, observer is inside the air, so that is 1. So he will say, the fish is at D by mu. So this is what will happen. So if you are in the water and the fish is in the water, you will think the distance is same. This apparent depth will happen only when you change the medium. When you go from water to air suddenly, because of refraction, you think the fish is at D by mu, right? So the observer thinks this is an observer in air. So if you ask this observer, right, boss, where is the fish? You can ask him more details. So let's call him observer 1 and observer 2. Observer 2 is in air, and you know what he will think? He will also think fish is in air. If the water is really clear, you can't tell the difference. Observer 2 thinks fish is in air at a distance of d by mu. This is the meaning of apparent depth. So the formula, right, apparent depth you are using only for 1 and 2. You cannot use the formula directly for the observer or the fish directly. It is for an observer who is inside the water, who is just inside the water and just outside the water at a distance of d by mu. Now, if you ask the bird, now see, this guy is in air, the bird is also in air, so then this distance was h. Then the bird will think the fish is at a distance of h plus d by mu. Is that making sense how we did it? You go one step at a time. You take the observer from the fish and move him towards the bird. Let me show the other one, the reverse. Now, this is the bird there. This is the fish. So this is your object, and this is the observer. So light rays are coming from the bird. This distance was h, and this distance was d. So if an observer is standing in the air, if you ask him, boss, where is the bird? He will say h. The moment you put his head inside the water, there is a refraction. What is the formula? H by mu object. Where is the object? In air, 1 into mu observer. Where is the observer? In water, into mu. Are you getting that formula there? So this person will say it is mu h. So the moment you put your head inside the water, suddenly you think this bird is at a distance of mu h. Now you are in the water, the fish is also in the water, so the fish will say it is mu h plus capital D. Are you getting how to use that interface of each medium? So here, when you're saying H apparent, you're only talking about that. So in this case, H apparent was what? H by mu object into mu observer. So the question is, who is the object, who is the observer? This is 1 and this is mu. That's how you're getting mu H there. Are you clear how we are moving the mediums? Any doubts on this? Clear? So that's one way. I'll give you a very general formula also, but remember this thing. It's useful. Like something messes up, you know how to do. You just jump from one medium to another medium. You just keep taking the observer. Take a break. Come back by 9:46. We'll continue from here. Any doubt so far? Chalo, come back in 5 minutes. Let's start off. Let's see one more. This is another standard model. Let's say we have a concave mirror, and this is filled with liquid. Refractive index mu. And this depth is some h. The radius of curvature is r. And you kept an object somewhere here. And this distance is capital D. So now what happened? This is a concave mirror filled with liquid. Find D if the final image forms on the object itself. Find the value of capital D if the final image falls on the object. Now, if I ask you this question, right, totally how many phenomena are happening here? The light rays will hit the water, so there is a refraction. Then they will hit the mirror, reflection. Then they'll hit the water again, refraction. Then they come back again. You're getting? There are three phenomena happening here: refraction, reflection, refraction. That is the meaning of a final image. So how do you do this? This is a really good mains level question. Standard model looks weird and tough, but think for a minute. I'll show you. Right, Param. This is the important thing. Huh? Whenever you hear this word, the final image is on the object, means what? The light rays have retraced, isn't it? The way they went, they must have come back. So whenever you hear that word, final image is on the object, meaning they hit the mirror along the normal. If final image is on the object, this implies rays have retraced. So the mirror thinks the light rays are coming from the center. So how can that be possible? That means rays are coming along the normal. So after refraction, जो भी light rays आ रहे हैं, they are coming along the normal. So the mirror will think the object is at the center. Mirror thinks it is not there, but that's what the mirror thinks. So again, let's go back to that story. Let's bring our observers. Let's ask this guy, observer one. Ask him, boss, where is the object? He will say D. You put him inside the water, and now if you ask him, boss, where is the object? He will say, okay, the formula is D by mu object. Object is in air, and mu observer, mu D. So he will say it is mu into D. Now the pole will say the object is at a distance of mu D plus H. Is that making sense? So the mirror thinks object is at mu D plus H. Now in a concave mirror, the only time when the object falls at the image is at the center. Which is at the center. There, that's it. That is the whole idea there. So mu d plus h is equal to radius r. D is equal to r minus h per mu. If you actually try to trace the light rays, this is how they would look. The light rays are coming like this. They're going from rarer to denser, right? So they're coming like this. They would go towards the normal. So when you extend them backward, this was the center. The light rays would bend this way, and the mirror will think these are coming from, a little far off. There. That's what the mirror thinks. The light rays are coming from the center. And then you know what happens? The light rays will go back again. Is this clear, everyone? So you can do this in 2 to 3 steps. So use the apparent depth and then finish it off. So the mirror will think this way. All clear with this? Next one. Let's say we have an observer, and let's say we got 2 slabs, mu1, mu2, h1, h2. Let's say t1 and t2. And the object is here. And let this distance be capital D and let this be h. Now, if you ask this person, boss, where is the object? What will he say? Find the distance of the object as seen by the observer. No, it's a good answer, right? While deriving it will look weird, but the final answer जो आएगा बहुत अच्छा आंसर आएगा वो. And you can remember the result actually. It'll be useful. I'll show you. If there are 10 slabs, like give it a try. Remember how to do? Bring that observer. Let's ask him where is the object. Then ask this guy where is the object. Then ask this guy. Then ask this guy. Then ask this guy. Then ask this guy. Yeah, it is a little long, but you have to keep asking everyone, and then they will see something. Try. I'll give you 1 or 2 minutes. It's useful. By chance you forgot in the exam, you should know how to derive. Okay, let's see. It's a little lengthy, but you'll do get a good answer, right, Samyak? Right, Aditi. See, so he is the observer. I'll draw a little big so that we can clearly see this is the object. So light rays are coming from the object. This is T1, this is mu1, this is T2, and mu2. So rays are going from this way. So you have to start from the object. So this is my observer 1. If you ask this guy, okay, where is the object? He will say D. Now, once you take him inside the glass slab, this observer 2 will say, now it is refraction. What is the formula? D by mu of the object, which is 1, and mu of the observer. So he will say it is mu 2D. If you go inside the slab, now see, as long as you're traveling in the same medium, nothing changes. You simply add the distance. Observer 3 will say it is at a distance of mu 2D plus T2. Is that making sense? So that formula is applicable only when you cross the medium. If you're traveling in the same medium, you just keep adding the distance. Are you clear with this? So if you ask the observer 2 and 3, where is the object? You know what they will say? They will say the object is inside mu2. They will think the object is in mu2. Now, if you go to observer 4, now there's an again refraction. Again, the formula mu2 d. So when you go from 3 to 4, this is what they will say. So mu2 d plus t2. That's what 3 things by mu of the object. Where is the object? It is in the medium mu2. That's, remember, if you ask observer 3, where is the object? He will say object is in mu2. So that's what he will tell the observer 4, right? He thinks object is in mu2. So that's why you got mu2d plus t2. So even 4 will think the object was in mu2, but now it came to mu1, so into mu1. Then if you ask observer 5, whatever 4 sees plus this thing, so if you divide this will be d by mu2 plus t2 by mu2 into mu1 plus t1. That d will cancel off, so that would be d only. Now if you ask this person 6, so he will say, okay, whatever 5 is seeing d plus t2 by mu2 into mu1 plus t1 by mu of the object. He will think object is in mu1 and mu of the observer, that is 1. If you divide by mu1, you end up with the mu1 will cancel. You get d plus t2 by mu2 plus t1 by mu1. Now if you ask the observer, the final answer will be h plus t1 by mu1 plus t2 by mu2 plus t. Did you notice that? That means literally you can replace each slab with t1 by mu1, t2 by mu2, and you're done. So it will feel as if the space got compressed. Clear? So yeah, we can do like that. It goes long, but the final result is good. So now we can extend this formula. I can make it more generalized. So let's say we have an observer standing in a medium mu_m. And let's say we have multiple slabs. And there's a distance also between them. And let's say this is the object here. mu1, t1, mu2, t2, mu_n, tn. Let this distance be h. Let this distance be d1. Let this distance be t2, and so on. And let this distance be dn. Then you can simply say the apparent distance would be h plus add all those distances. So that space in the middle is useless. You can just remove all that stuff. Again, we are keeping all in the same medium, mu m, everywhere it is mu m. So on till dn plus t1 by mu1 into mu medium. So since you're in a medium, t2 by mu2, mu medium, and so on, tn by mu n, mu medium. In the previous case, I took outside vacuum, so that mu m didn't come. So this is the formula. H plus sigma di. So this is all the distances which are in air. You can add them, all these distances. Plus mu medium into sigma ti by mu I. This is your apparent distance. Just be careful with one thing. Object and observer are in the same medium. This is also mu m, this is also mu m. If that is not same, then you're dead. You have to go back to the basics again. Object and observer are in same medium. So remember like this. You can simply compress this slab into T1 by mu1 into mu m. Making sense? So replace that medium with a region of T1 by mu1 into mu m and you're done. You can remove the slab. So T1 becomes this. And then it becomes easy from there. So are in same medium. Helps you when if you have 2 to 3 slabs. All clear with this? Now, based on this, we have something called apparent shift. That means when I put a glass slab between you and the observer, you think the object shifted. It actually comes from here only. So if I take one slab for simplicity, I'll show you this first. Let's say this is mu and this is t and the object is here. And the observer is here. Let's say this is mu m and mu m. This distance was t. This distance was some d1 and this distance was d2. Just now we saw the formula, the apparent distance. Was d1 plus d2 plus t by mu into mu m. Isn't that the formula? Just add all the distances. Slab becomes t by mu medium. So this mu is the slab. What was the actual distance? So the apparent shift is the actual distance minus apparent distance. Where it is exactly and where do you think it is there? Now when you subtract them, you can clearly see the actual distance is d1 plus d2 plus t. This was the actual distance. The apparent distance is d1 plus d2 plus t by mu slab into mu medium. This is even better formula because you can completely ignore all the other distances. And then you end up with the apparent shift will be t into 1 minus mu medium by mu slab. If you ask me, even a better formula there. So whenever I put a glass slab between you and the object, you think it got shifted by this much distance. Clear with this? One more thing, which direction, like which way did it shift? Did it shift away from me or towards from me? So this is the thing you should remember. So if you have a slab, this was the object. So the light rays would go like this, and they become more closer, and they would go like this. So when you extend them backward, it will feel the light rays are coming from here. So this is your O dash. This is the shift. So O dash is given by T into 1 minus mu medium by mu slab. What if the light rays are forming a virtual object? Meaning, let's say this is the slab. The light rays are coming like this. They're meeting after the slab, meaning the light rays would have gone here and they would have met here. So it's a virtual object there. Again, the same thing. So when they do refract, they would go like this. They would actually meet somewhere here, O dash. This is the shift. So it's easy way to remember. Remember like this. The shift happens always in the direction of incident rays. What is the direction of incident rays? Left to right. So shift will happen towards right. What is the direction of incident rays? Towards right. The shift will happen towards right. You're getting it? That's an easy way to remember. The shift is always in the direction of incident rays. So you will shift by this much in that direction of incident rays. The shift is in the direction of incident rays. Object and the observer must be in the same medium, or else that mu m thing will get messed up. This is what I said. You have a bunch of formulas. You should know when they will work and the results. Clear with this? You can even extend this further. So what if you have multiple slabs? And if you observe, this shift doesn't matter. What is the distance between the slabs? So if this was T1, mu1, T2, mu2, Tn, and mu n, and let's say all these mediums are mu m, meaning the space between the slabs, you have dipped this entire in this thing. Then we have a general formula. The apparent shift is given by summation Ti 1 minus mu I by mu medium by mu slab. This is independent of distance between the slabs. So it doesn't matter where you keep the slab. So if I take a slab between you and object, I keep it close to you or close to the object or in the middle, the answer will remain same. You will see the shift is same. This is your shift. This is the apparent distance. This is where you think it is. This is what you think it shifted by. Technically दोनों वही से आ रहे हैं. Is this clear? Everyone clear with the formula there? Let's see how they'll frame a question on this. So this is apparent depth ka one variation there. So let's say we have a concave mirror. The radius is 20 centimeters. We have an object here. This distance is 31 centimeter. And you went and brought a slab and you kept it in the middle. This is 2 centimeters. And let's say mu is equal to 2. Find the final image. Now, when they say final image, the first question is this: how many phenomena are happening? Light rays are hitting the slab, apparent shift, then they hit the mirror, reflection, then the light rays will hit the slab again apparent shift, and come back. That's your final image. So the light rays will go through the slab twice. Get me this answer. And there's no kinematics. I don't know. What is the formula? This is the formula. T into 1 minus mu medium by mu I. Here, medium is not given, so it's all vacuum. So when you do for the slab, don't care about the mirror. When you do for the mirror, don't care about the slab. Let's see. 15. Okay. Let's do one at a time. So first thing, what will be the shift? So if you ask the slab, T into 1 minus mu medium by mu slab. That would be 2 into 1 minus half, 1 centimeter. That means the light rays which are going from here, whatever they do, it will feel they are coming from this position here, O dash. This is the shift. So if you ask the mirror, boss, where is the object? So if you ask the mirror, where is the object? Mirror does not know who is O. It will think light rays are coming from O dash. Now that is a distance of 30 centimeters. Apply the mirror formula. Right rays are going to the right side, so that is positive. 1 by V plus 1 minus 30 is equal to radius is 10, 1 minus 10. This would give you V is equal to minus 15 centimeters. Perfect. So these light rays are going here and they're meeting somewhere here. This is your image. Let's call it I1. Now, if you ask the slab again, boss, where is the light rays coming from? The slab will say, the light rays are maybe somewhere here. I1, they're coming this way. So when they go here, again, they will shift. So when you pass through that, there will be a shift again. Which direction? In the direction of light rays. This is your I1 dash. And this shift is again 1 centimeter. So what is the final answer? This was 15 centimeters from the mirror. And you shifted 1 centimeters forward. The answer is 16 centimeters from mirror on the left hand side. Is that making sense, everyone? So every time you pass through the slab, you will shift 1 centimeter in the direction of incident rays. So initially 31 becomes 30. Then 30 will give you 15 from reflection. Now the 15 is passing through the thing. So anyone who is standing here, he will see I1 dash and he will think it is at 16 centimeters. Is that clear, everyone? So when they say, right, final image, generally you have to get it after all reflections, meaning the observer is standing somewhere here. So after once the light has come from the slab, nothing else is going to happen. All clear with this? Any doubts on this? Definitely make sure to go through this once. Like they're not tough, but you should get used to the formula there. Let's say we got a slab, x is equal to 0, x is equal to L. This slab has a variable refractive index, mu is equal to 1 plus x by L. So the refractant is changing from 1 to 2. Object and the observer. Find the apparent shift. How do we do this? At a distance x, take a thin slab. The slab is so thin, I can assume mu is almost constant. So this thin slab will give you a small shift. You have to integrate all the shifts. Remember that summation sigma that becomes an integral. This will be the thickness of the slab is dx, 1 minus mu medium, that is 1 by mu of the slab. Which is dx by 1 minus 1 by 1 plus x by L. So the total shift will be, integrate this, dx 0 to L minus dx by x by L plus 1, 0 to L. This would be L, and this integral will be, I hope you guys remember that integration. Dx by ax plus b का integral is 1 by a ln ax plus b. So a का place में we have 1 by L, so L goes up there and you get ln 1 plus x by L. Limits will go from 0 to L. Put 0, you get ln 1, which is gone, and this is L ln 2. L into 1 minus ln 2. Is that clear, everyone? Yeah, right, Samya. Right, Arya. So that's what you do. You can treat this as a infinite multiple slabs and you find shift due to each one and add it up. It's kind of like this. You're doing summation of all the slabs ka shifts. So if you have a variable refractive index, this is how you handle it. All clear with this? Next one. If you see, right, there's nothing like two big questions and all, one or two, but most of them are like this. This is another good variety there. Let's see how will you handle this. Let's say we have a tank filled with a liquid. You're standing outside. The object is here at rest. Someone started pouring liquid into the container. The surface rises with speed v. So this liquid surface is going up with v. Find the speed of the object as seen by the observer. Observer is not moving, object is not moving, but that interface is moving. Refractive index is mu. Find the speed of the object. This is a good mains question. Let's see how you do this. Yeah, that's a bit of a kinematics if you want. Motion with refraction. Hope the question was clear. Listen carefully. This is a classic trap. This is what people goof up. They think, yeah, height is changing. This is a mistake that happens. So when the liquid is rising here, there are actually two things change. Go back to the basics. Let this distance be x and let this distance be y. If you ask this person, boss, where is the object? What will he say? Remember, this is the observer. So let's ask this person here, 1. He will say, where is the object? X. If you ask this person, where will he say? He will say, it is at a mu x. So where will the observer see? So the apparent distance. So the mistake here is people think only x is changing. This is mu x plus y. I think I wrote reverse. That is x by mu. So when the water level is rising, x is increasing, but the distance between the man and the level is also changing, isn't it? So two things are happening. Now, when you want the apparent speed, you have to differentiate this quantity. This would be 1 by mu dx by dt plus dy by dt. Now ask yourself, when the water is going up, what is happening? X is increasing, so dx by dt is plus v, since x increases. But y is decreasing, so dy by dt is minus v, since y decreases. This will become v by mu minus v. That's your answer. It's actually a negative thing. Means we are thinking it is coming up. No, it's actually going inside. So most common mistake is people don't take that y. They take only x by mu and then they differentiate x by mu and you get v by mu. You're getting the velocity, right? That h apparent. Remember what did I say? H apparent is the distance from the interface, isn't it? That means the answer you get is a relative velocity with respect to the interface. So what I'm asking is ground frame. Is this making sense? Same question. Let me make it even better. If you do this, I think you understood these kind of models. Now, let's say when the water level is rising, the object is going up with V1, the liquid is going up with V2, the observer is coming down with V3, all are moving. Now find the apparent speed as seen with the observer. You just have to be careful when you're differentiating what you're getting actually. And then the idea is easy from there. Now, if you're right, the equation is still the same. This is x, this is y. So when you get the H apparent, x by mu plus y. So the apparent speed is 1 by mu dx by dt plus dy by dt. Now the question you need to ask is this. Look at this thing. What is x? X is the distance between them. So keep it very simple. What is V1 doing? Is V1 increasing x or decreasing x? When the object goes up, what happens? X is the distance between the object and the interface. It is decreasing, so minus V1. If V2 is going up, what is happening to x? It is increasing, so plus V2. What is y? Y is the distance between object and the observer. When V2 is going up, what is happening to y? It is decreasing. When V3 is coming down, what is happening to y? It is decreasing. Plus ho gaya. Are you getting it? So that is how you can figure it out. You can say relative velocity, but this is better. What is V1 doing to x? Decreasing. What is V2 doing to x? Increasing. So plus minus. What is V2, V3 doing to Y? Both are decreasing, both are minus signs. So that's the reason we keep negative. So both decrease Y. Right? So here this is decreasing X and that is increasing X. Is this making sense, everyone? Yeah, so it looks scary, all are moving, but you can handle this. So once you know that thing, you're differentiating X and Y, you can figure out from there. Any doubts on this? Then we have something called optical fiber. So let me just show you that. I'm sure you must have seen optical fibers. The internet connection you have, if you go and break the wire, the internet goes off, but inside you will find cables like this. In the actual picture, right, if you look at one cable inside, it looks something of this sort. So we have a core inside, then we have a plastic coating, then we have a cladding. So all this is a protection. So this inside thing, this is your main optical thing there. So the whole internet, right, transfers all because of this thing. You must have also seen this in some toys. There's a toy like this. You put some bunch of optical cables and put a light at the bottom. The light passes through the optical cables. Ever seen this? So, so if you see, right, somewhere in 2000, during you guys were not born, there is something called an internet boom. 97, 98, 99, people were going crazy about internet the way right now people are going crazy about AI. So during that time, right, every company, yeah, meaning if you're an internet company, you're like, people used to put money, a lot of money on you. Just imagine, like, someone is, selling milk. They just put, milk internet company and done. That's it. Suddenly the valuations have gone up. So it was pretty crazy that time. So during that time, everyone thought, the future is internet, everything is going to change and all. And people started building hell lot of optical cables. I still remember, I think in 2005, 6 time when I was in school, Reliance was literally digging everywhere. Reliance has around 125,000 kilometers of optical cables. 125,000 kilometers of optical cable. This is 6 years old data. Now they must have been doubled. So everything right now, when I'm speaking to you, right, you think it is wireless. It is not. When I speak to you, the signal goes through my router and it goes to the nearest geo tower. From there, it goes through an optical cable and goes to the server. From the server, it gets there and then it comes with an optical cable to your nearest center at your house. And from there, it is sent as a signal again. So everything that you're thinking about is passing through optical cables. This is like your internet ka highway. So if you're accessing something, if you're talking to someone in Dubai, right, we have a substation in Mumbai now. Previously, we never had it. If you're doing a Skype call to US, our servers used to be in Dubai, but India said no, boss. If you're doing something in India, your server has to be in India. So the signal comes from directly, right? So you're talking to someone in US, the signal goes from US to Europe, Europe to Dubai, and Dubai to Mumbai. So there is a lag. This is what we call as a ping. Ever seen this? If you're playing a game, you must have seen this term ping. It is generally in milliseconds. So if you're playing a game with someone in Dubai, you will have a ping of 20 to 20, 30 milliseconds. That means when he does something, it takes you 30 milliseconds for you to receive it. Now, even when I'm talking to you also, right? I wrote now. See, when I wrote it and when it came here, I can see the difference. There's a small ping, maybe in milliseconds, but it is there. Right? Now, but the same thing, if you place with the same guy in Dubai from Assam, you get a ping of around 80 to 100 milliseconds. That's because the server will go from Dubai to Mumbai and Mumbai to on the land, it goes through India and goes to Assam. So it is a more delay there. So you get a ping like that. And we have all over this thing. I did send you a video in the last time. If you see the globe, right? If you see, just like we have highways, we also have optical cable highways. This is the map of an optical cable, little old one. So every day there are ships which are laying optical cables under the sea. These are all the optical cables. And see the bunch of network between Europe and US. Huge lines. And if you see the India Kenya lines, we are getting like this. So we have lines going to Singapore, Southeast Asia, and this thing. So All these optical cables are under the water. So that way, so if there is a war or something, that Iraq ka war which is there with the Trump, they have actually threatened to cut off these optical cables under the sea. Yeah, we'll still get net from somewhere else, but yeah, you can do all that. So we are laying all these lines and everything. So the whole internet works on this. Currently, there's a huge shortage for optical cables because once you got this AI and servers and all, the optical cables were literally getting consumed and everything. And second thing, in Ukraine war, these people, right? You can hack a if you're using a drone with a Wi-Fi or something, you can hack it, or you can send some signals and disrupt the Wi-Fi, and the drone will get distorted and it will not go to the target. So what they do, the drone which is there, and just assume this is a drone kind of thing. On top of the drone, you have a small spool of 3 to 4 kilometers optical cable. As the drone is going forward, the optical cable keeps coming down. And we have an operator here who is operating the drone through the cable. Literally, it is connected with a wire. You cannot hack this. You cannot interfere with this. That means as the drone is flying, you will see a thin cable in your air. Like it's like a kite and a string. Now in Ukraine, right, these people are flying the drone so much. The whole areas, right, are filled with optical cables ka net. Birds are using these optical cables to bird nest, build nests. So every drone uses 2 to 3 kilometers of optical cable. Just imagine. And once the drone gets destroyed, I get a new one. So optical cable is used everywhere. Construction, internet, these wars also they're using this. For every drone, there's an optical cable now. So there's a huge shortage right now. The prices have gone up almost 8 times. 8 times. The price used to be like what? 1,000 rupees before, now it's 8,000 rupees. And there are only 12 companies in the world which manufacture optical cables. In India, there's only one company. So yeah, if you see this underwater cable, right, it looks something like this. I think this is there. Can you see that big wire there? That is how it looks under the water. So there are ships which are laying this cable under the seabed. So that is an optical cable there. I'll just tell you the small theory there. So how does this work? The idea is pretty simple. You send a light ray inside at an angle greater than theta critical. So this is mu1, this is mu2, this is denser, and this is rarer. So when you send a light ray here at an angle of incidence I, once it enters here, this will be R. So when this thing goes and hits this surface here, if you can make sure this angle 90 minus R is greater than theta critical, what will happen? The light ray will bounce and bounce and bounce, and this angle will be always 90 minus R now. So once you hit the critical angle, you will just keep on hitting critical angle and so on. This will keep bouncing. And the signal will travel with the speed of light inside this thing. So you can and transmit in one optical cable, you can transmit 1 lakh signals. 1 lakh signals. You can connect 1 lakh connections, telephone connections with one optical cable. You can't do that with a copper wire. Copper wire will connect only one connection with one copper wire. So this thing can carry huge density. So all that 4G, 5G we talk about, it works like that. So when you use Snell's law here, sin I is equal to mu1 sin R. That's your equation 1, and we have sin R is equal to 1 by mu1 sin I. The second thing, the sin theta critical will be mu2 by mu1. Now, if you want the light ray to bounce inside, 90 minus R must be greater than theta critical. So whatever you're talking and all, these are converted, the electric signals are converted into light and then they're transmitted inside. So this is basically your TIR. If you put sine on both the sides, we get sine 90 minus R is greater than sine theta critical. Sine 90 minus R is cos R. Sine theta critical is mu2 by mu1. Cos R is nothing but root over 1 minus sine square R. And sine R is nothing but 1 by mu1, this thing. So that would be 1 minus Sine square I by mu1 square is greater than mu2 square by mu1 square. From here, we get sine I is less than sine inverse root over mu2 square mu1 square minus mu2 square. There. So this was your incident ray. So if you satisfy this condition, the light ray will bounce inside. That's it. So really not much on this, but this is the idea in optical cable. So the light rays which you're sending inside should be sent with an angle less than this, which is sine inverse root over mu1 square minus mu2 square. All clear with this? That's your optical cable, again based on refraction. So what we did all today is refraction on a curved surface. So next class when we catch up, we will do refraction on a plane surface we did today. We'll do curved surface, and we'll start off with the lenses also in the next class. So yeah, I think that's a bit about it. So we have done almost 29 questions. So make sure to go through the notes. You have to start solving. I think mirrors and refraction on curved plane surface, start doing it, because next week we'll finish off majority chapter will be done. After that, what is left is a little optical instruments and stuff. So maximum 3.5 classes, we should be able to wrap it up. Okay, with that, we'll wrap up for the day. And do remember, there's a test online, so make sure to give it tomorrow. So any doubts, anything else, please stay back, or else you're free to leave. I'll see you again next Tuesday, same time. So take care, stay safe.